There we go. Any questions on this first bunch of stuff? Local linearization looks like this. Right? Here's the formula for calculus 1. If it's a tangent line, the line has this goes through the same point on the function x0, y, f of x0, and with the same slope as the original function, we can make a second order approximation like this. This is the unique second-degree polynomial that fits the point, the first derivative, and the second derivative of the original function. And now that motivates us to go a step further, provided the function has all these derivatives. You come up with the following theorem. We'll say similarly, the nth order polynomial, let's say nth order, different between orders have an nth power term. Order has at most an nth power term. So this, when I say order, it may or may not have the highest power of the polynomial. So in general, it's an nth degree polynomial. We'll say nth order in case the highest power is 0. The nth order polynomial approximation to a function y equals f that has n derivatives is called nth order Taylor polynomial. Now, I've done this reverse from the book. The book does the Maclaurin polynomials first and then does the Taylor polynomials. You can do it either way, and I'll show you in just a second. And here's what you do to get generalizing that. And all you have to do is take the function in its first n derivatives. So with n derivatives, and this matches f at x0. Its value does. Derivative matches f prime at x0 all the way down. For the nth derivative, I'll put parentheses that means derivative at x0. So it matches all those derivatives at x0. And it is P n of x is the notation the book uses. And it is f at x0. It looks like local linear approximation, right? F at x0 plus f prime at x0 times x minus x0. It's a local linear approximation, right? This was just L of x. And if you think about it, we added this to it. F double prime of x0 presenting it this way times x minus x0 squared. What is this? That should look familiar, right? I hope. This one altogether, in reverse order, is 2 of x. The second order polynomial that matches the function its first and second derivatives. And then you just keep going. You add f triple prime at x0. By the way, 2 factorial. Remember factorial, how that's defined? N factorial. You haven't seen it before. Good chance you haven't at this point. Means n times n minus 1 times n minus 2, all the way down through 2 times 1, all multiplied together. That's its definition, right? That exclamation mark called factorial. I'm going to use that in here. Instead of saying divided by 2 like I did in Q of x, I'm going to say divided by 2 factorial, because after all, 2 factorial is 2 times 1 is 2, right? 3 factorial is 3 times 2 times 1 is 6. 4 factorial is 4 times 3 times 2 times 1 is 24. And these things get really big. Actually, the factorial function is really fast growing. If you take 70 factorial, for instance, on a lot of these calculators, it's too big because this is already big than 10 to the 100th power. It's bigger than a Google. 1 followed by 100 zeros, just multiplying 70 factorial out. If you would take 100 factorial, blow off, your calculator, give an overflow error on almost any calculator you have. So these numbers get big really fast. This is already bigger than astronomical. It's bigger than all the atoms in the known universe by many orders of magnitude, actually. So factorial goes really fast, just to give you a hint here. But that's its definition. And we take f triple prime over 3 factorial times x minus x squared, cubed, excuse me, plus so on and so forth. You can see the pattern now, right? This is how we define the nth order Taylor polynomial for a function f of x, for a function at a point x equals x0. It matches f and its first n derivatives. When you take the derivatives of this polynomial, it has the same derivatives and same value of the function at x0 that the original function had, f of x. All right, any questions on that? That can be equation 3 of something called 1, local linearization, 2, the local quadratic, and 3 can be the general formula. And I should have said this doesn't go on forever. If I want the nth degree one, this is up through fn at x0 over n factorial x minus x0 to the n. On the next section, we will let those go on forever. We studied infinite series just so we can do this kind of thing, partly so we can do this kind of thing. All right, so there's the nth degree polynomial. It stops at nth power of x is the highest power. All right, I'm going to erase it if there's no questions yet. A lot of this section is not too bad because the first, most of it actually, is just calculating. Let's see the theory behind this, you know how to use it. I can't tell you how frustrated I was being real interested in physics and taking physics classes as a graduate student. I took quantum mechanics and satellite and perturbation theory and classical mechanics and symmetry groups in physics. And I over and over found again, I'd see these neat math formulas, they'd never motivate them. I didn't know when they worked or if I could use them. And it was very frustrating. Although the math classes were frustrating too, because frequently we never did any application whatsoever what to use it for. And eventually by studying this stuff more and more after I finished, I kind of figured most of that stuff out. But it's really hard to get it in. Sometimes I think my math professors didn't understand any physics, and physics professors didn't understand any mathematics. Maybe that's why, but physics, they always seem to use circular reasoning to prove their math result. They say, this is because of this, because of this, because of this. Isn't that what you started with? You know, it's like the hole in the bucket problem. But my classical mechanics teacher, I remember, did that. And I thought, that doesn't show anything except that it made, doesn't make a contradiction in those things. All right. So, all right. Here's a real simple example. Find the third order actually, yeah, all right. Taylor polynomial for this easy function. This is actually about the easiest one we can do. F of x equals at x equals 1. How about that? What is a third order Taylor polynomial? It'll almost surely be third degree, third power, at x equals 1. What would approximate e to the x really well when we're close to x equals 1? And the idea here, as you saw in the picture, if you take a function and make this approximation, maybe here's y equals f of x, when you're close to x0, it does a pretty good approximation because it matches the function, all its derivatives, starts to look just like the function. But as it wanders away, it may do very different things because it's missing those higher powers, right? It only goes to the nth power. And if your expression depends on higher powers, then eventually as x gets big, the higher powers overwhelm the lower powers, and this thing goes askew all over the place. So it's a real good approximation close, just like the local linear approximation was good if you were close enough. Those are good if you're a little further out, but every one of these, as long as you have a point at this, it tends to digress. I mean, obviously, if it's a polynomial exactly, because it is a polynomial, it approximates itself in that case. But in general, it tends to go on. All right. So what is this one that will approximate the exponential function when I'm near x equals 1? This will be a third order Taylor polynomial. I already know it's going to mess up. How do I know it's going to mess up when I get far out? It's because y equals e to the x looks like this, right? Exponentially growing function. At x equals 1, it's equal to e. And so it goes through 1e. And if I fit a third order polynomial through here, highest power is cube, what's going to happen with the end behavior? On this end, it's going to go up, 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 right? And then it might do something like this. But on this end, it's going to go down, 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 which is not what the exponential does, right? It decays to an asymptote. So eventually, this is going to be wrong. It's going to be a third order polynomial, something that looks like this. Here's all third order polynomials can do. They can't do anything else. Remember, they can look like, if it's got a third power in it, a third degree polynomial, it can look like this with a wiggle. It can look like this, just flatten out, that horizontal tangent here. Or it can go like this, and that's all it can do. If it had more than 2 local minima and maxima, then it would have, right, you'd be able to find more than 2 critical points. It has to be higher than third degree. Remember, to take the derivative of a third degree polynomial. If you take the derivative of third degree polynomial, you get a second degree polynomial. It only has at most 2 spots where it's 0, so there's only at most 2 critical points, right? So we're going to have 2 or 1 or 0, and that's it with a third degree polynomial, because its derivative only has at most 2 solutions, 2 values where it's equal to 0. All right, so knowing that, I think this approximation is going to go like that, or it might just flatten out and go down forever, but it's going to be bad eventually. But near here, it can be very close, is the idea. And here's what we can do to calculate by equation 3. We need to use f at 1. Well, let's just e to the 1. What's f prime at 1? Well, let's calculate the derivative. I told you this is the easiest function. F prime of x is its derivative, remember? F double prime is e to the x, forever. All of its derivatives are equal to the original function. That makes it very easy. Because now f prime of 1 is also e to the 1. F double prime of 1 is e to the 1 equals e. And f triple prime 1 is equal to 1 is e. So all the derivatives at 1 are equal to e. And now, by 3 with these values, we get that P3 of x, the third order Maclaurin Taylor polynomial, is what? It's equal to f at 1 plus f prime at 1 times x minus 1. 3. This is it with x equals 1 plugged in. That's all it is. Plus f double prime at 1 plus f prime at 1 for 3 factorial times x minus 1. Just made it, right? So there's the answer. But I need to find out what those values are. Fortunately, I found that all those values are e, right? So I can say it's actually equal to e plus 1 plus e over. By the way, you can make this formula a little more palatable, maybe, if you think about it, by putting this over 1 factorial. Factorial is equal to 1, right? It's just 1 multiplied by itself. And this one, you can actually also write 0 factorial, because in addition to that definition I gave you, we define 0 factorial equal to 1. That way, each factorial, like if you take 1 factorial, is just 1 times 0 factorial. 2 factorial is 2 times 1 factorial. 3 factorial is 3 times 2 factorial. That's 3 times 2 times 1, and so on. It follows this formula, and all the formulas work out nicely if you just define 0 factorial equal 1 also. So n factorial is the first n numbers multiplied together, and 0 factorial. Okay. And they'll put those in, and you put those in here, and then the formula is very nice, right? 0th derivative over 0 factorial, first over first 1 factorial, second over 2 factorial, third over third factorial, up to whatever power you have. In this case, that's the n. What I have here now is e that's x minus 1 squared plus e. Oh, this is over 2. So. And 3 factorial x minus 1 cubed. 2 factorial is 2, 3 factorial is 6, 1 factorial is 1, 0 factorial is 1. There it is. This is the polynomial. Now you can multiply that out, and with some work, if you multiply it out by algebra, yeah, well, there's an x cubed times e over 6. So we're going to get, actually, everything's multiplied by e. So I just take it out. And I get times x cubed over 6. And then here, this is pretty complicated. It's x cubed minus 3x squared over 6 makes this one minus 3 plus 3 minus 1 all over 6. That looks like. This one looks like third minus all over 2. Looks like 1 and so forth. So the x cubed terms, there's only one of them. X cubed over 6. X squared terms, there's minus a half x squared. Plus a half x squared is nothing. So that's no x squared terms. I should write this out. Put this one on the top. How about? We'll multiply it out. Let's write this out a little bit so it's clear. E times x e. All right. So the x cubed term, there's just this over 6. We get e over 6 times x cubed plus times all this stuff minus 3 6. No more x squared term, so there's plus 0 x squared in this one. And then x, there's an x here. Minus 2x over 2 is minus x. They cancel. But then plus 3x over 6 is plus a half x. All times e. I should this be multiplied. Literally. So it's plus a half e. And then the constant terms. 1 times e minus 1 times e. Then I got plus 2 minus e over 6. That makes e over 3. So this is right here, or even right here, the Maclaurin polynomial of degree 3. It's just you have to multiply it out to its standard form to simplify it, right? A number times x cubed plus a number times x plus x squared. It's a number. You can leave this one off. What's the right x? And now if I sketch that with my calculator or something, some of the problems in there say sketch with your calculator. I've thought about this and decided to leave that off. I don't think that's an important thing to spend your time on. It takes a lot of time. It is really useful to see the concept. And that's what I've tried to do here. But I think if you understand this concept, then you don't need to actually sketch some of these. But that's what it happens. It's just what we said here. It's a third degree polynomial. It's going to go like this. Looks like this one doesn't do the, maybe I should draw it again. Looks like this one doesn't quite go like that. Looks like it comes something like this. Now you remember exponential growth is fast. It's faster than any polynomial growth. We did that. You did that limit thing last semester. Or if you take the limit as x goes to infinity of any exponential function like e to the x over x to any power, 1,000th power, which one goes faster? This limit is actually infinity because e or any number bigger than 1 to the x power grows faster than any polynomial. This limit is always infinity. Or if you turn it upside down, the limit's always 0. So we know the exponential is eventually going to go out to outgrow the polynomial. The polynomial fit something like this. No, I don't think so. There's polynomial, something like that. And then because it doesn't have an x squared term, it's actually going to go something like this. It's the case where it doesn't ever flatten out. It's going to go something like that. It will actually eventually digress and not approach this asymptote the exponential function does. So there's the approximate fit. It's real well in here. It goes to the point of the function, 1e. It has the same slope e, the same second derivative e, and the same third derivative e. That's the original exponential function. All its derivatives are e. Right? It's easy to remember. At 1, they're all e. But then eventually it gets outgrown over here, and it dives down to minus infinity here, where this one approaches an asymptote. Any questions on that? Baby problem, maybe, but it really illustrates the concept nicely. All right, so that's one of them. Now it turns out that the most important case of these Taylor polynomials is when the point of expansion, we call it x0, is 0. That's a special case. And why is it so important? And the main importance is just that it's much easier to write down. It's less writing. And because that, everybody's tabulating all sorts of books of these things at x equals 0. And there are plenty of other important series that are at 0, but most of them at 0 to make convenient. When they're not at 0, they're just translate them to 0 to make them easier to write. So that's the idea of the whole thing. Getting something to write down, because as you can see, these are complicated, right? Trying to multiply these out of life is just a mess. I'm starting to see it already. It's getting hard. I need to get my alcohol back. Don't you want anymore? Now, special case, when the expansion point x0 is 0, equation 3 comes. This is the special case of the Taylor polynomials. T(n) of x is the nth degree Taylor polynomial at 0 is f of x0. I'm sorry, f of 0 plus f prime of 0 plus f double prime of 0 over 2 factorial x squared. Minus x0 squared is just x squared plus f x0, I can write 0 every time, so that saves writing, over 3 factorial x cubed. And believe me, when you have x minus a number to cube, it becomes a mess, just like in the last one. We start taking x minus a number to the 10th power, right? It's just all over the place. So this one is multiply out. And this is a nth order Maclaurin mathematician. On the internet and see what they do in their lives. They're very fascinating personalities and so forth. makes mathematics much more interesting when you see some of these stories of people, Newton and so forth, and uh, who invented the calculus and Leibniz, and they were worthy of their reputations. A lot of them. They really did some fascinating stuff. And so here's Maclaurin's polynomials. And so the Maclaurin polynomial is just a case of Taylor polynomial when x is equal to 0. More than that, right? That's why I introduced the other one first. Look, does the other one first because this one first because it's easier, and then uses that to motivate Taylor polynomial. It's a special case of Taylor polynomial. Now let's try something a little more interesting. Let's try and find a Maclaurin polynomial. Find the fourth order Maclaurin polynomial for y equals cosine. About that. I don't have to say at x equals 0 because Maclaurin already assumes that. Right? What do I get? Well, I need to do the same thing. I need to calculate the derivatives. This time they're not just the same function over and over. Right? If I call this f of x, then I need f of 0. Well, first let's do the derivatives. F of x is cosine x. F prime of x is its derivative minus sine x. F double prime is the derivative of that is minus cosine. F triple prime is the derivative of that is the sine. And the fourth derivative, I'll write F4. If you get more than 3 scratch marks, it looks pretty hard to read usually. Fourth derivative of x is back to cosine x. And now you can see something interesting. On this function, it repeats, right? Now I'm going to take the derivative and get minus sine, minus cosine, sine, cosine over and over. It repeats every fourth derivative on this one. So what's going to happen here if we want to do higher degree polynomials, we could do it easily because it's just a repetitious set of derivatives, right? So this isn't too much harder than the last one. Now what we really need for the Maclaurin polynomial is f of each of these f and its derivatives at 0. So f of 0 is cosine 0. Oh, it's 1, right? F prime at 0 is minus the sine of 0. That's 0. F double prime at 0 is plus minus 1. F triple prime at 0 is plus sine of 0. At f fourth derivative at 0 is again the cosine of 0. So there's the first 4 derivatives at 0 that I need. Now if I call this 4, the equation for the, oh, and I should have, I put plus dot dot dot, I need to stop it at power, but I call it the nth degree thing. So this is up through nth derivative at 0 over n factorial x to the n. So should have stopped that there. If you don't stop it, then it goes on forever. It's called the Maclaurin series. So we're going to talk about that shortly. Okay, maybe next time. Hang on fast. Well, you can go on forever as long as the function has arbitrary derivatives, right? Let's try this one now. Right? Fourth order Taylor polynomial, Maclaurin polynomial for cosine x. So P4 of x is f at 0 plus f prime at 0 times x plus f double prime at 0 by 4. F double prime at 0 over 2 factorial squared plus f triple prime at 0 over 3 factorial x cubed. Oh, so what is that? F at 0 was 1. F prime at 0 was 0. plus f double prime is minus 1. So minus 1 over 2 factorial x squared. Oh, I forgot my one here. Plus f fourth at 0 over 4 factorial. All right, plus 0 x cubed plus the fourth derivative is 1 goes over 4 factorial x to the fourth. The fourth order Taylor polynomial that fits the cosine function and its first order special case of the Taylor polynomial called the Maclaurin polynomial. So this is equal if you just figure it out. See, now we don't have to multiply so much. It's just immediately 4 factorial is 24, so it's 1/24 x to the fourth minus 1 over 2 factorial is 2, so minus a half x squared plus 1. There it is. There's what fits the cosine function. If you think about it, this doesn't wiggle up and down forever like the cosine, right? Cosine looks like this. There's pi where it's equal to minus 1. There's minus pi where it's equal to minus 1. And then we're fitting the polynomial, so it's the fit at x equals 0. And if you look at the end behavior, the fourth power dominates. So on the end, since this is a positive number multiplying x to the fourth, it's going to go up on both ends, right? That's the dominant term analysis from algebra. But this is going to drive it down a little in the middle. And this says when x equals 0, it's at 1. So it starts right here. X equals 0, y equals 1. Just plug in x equals 0, and you get the point 0, 1. And it should fit this real closely. This x squared term dominates this one for x very small, right? The fourth power very small number is smaller than the second power. So it initially starts a downward parabola pretty close right on this cosine function. But eventually, this one overpowers it and tries to come back up. I don't know exactly what it looks like, but something like that. But it fails to keep following it. Looks something like that. It's symmetric also, right? This is an even function since it only has even power, so it flips over the y-axis and lands on itself. Maybe you remember those graphing things from algebra and calculus 1. But it looks something like that. It follows it pretty closely for a while and then it veers off. That's the Maclaurin polynomial. And if you carry more terms, you could start to make more of those humps out of here, right? If you get the 10th order polynomial, you could come close on a bunch of these things. In fact, it turns out if you let this go on forever, then it's called the Maclaurin series, and it's actually exactly equal to the cosine function everywhere if you let it go on forever. That's what the beauty of this is. By taking enough terms, you can approximate it as far out as you want. The trouble is that when you go out to 1 billion or something, it takes an awful lot of terms, awful lot of computing power to approximate it accurately clear out there. So people hardly ever do that. Instead, they'll do, if they need to approximate the cosine function way out there, they'll take the Taylor polynomial way out near there where it's good nearby, and they'll use that for the approximation out there. They'll use the Maclaurin polynomial when they're looking at approximating some function like cosine near 0, and then some other way out there. It was very fun when I was a student like you. Calculators were still young, and there were calculators that used some of these series approximations, not necessarily Taylor series very much, but series like these, and made some mistakes. And this guy going around giving lectures came by at a fascinating lecture on why calculators, how you could get your calculator to mess up these series and so forth that didn't work right at certain points. So anyway, this has applications in approximation theory such as computers. Good on that? That's the main thrust of the section. But there's one more thing. I mean, whenever you make something, you build a house, you want to know not just that it's good, you want to know how good is it, right? How good is this thing? Maybe I want to get 3 significant digits in my approximation. How can I guarantee it? There's a remainder. After all, because the Maclaurin polynomials are just a special case of the Taylor polynomials. The theorem applies to both, right? So I'll say this for the two of them. And here it is the remainder theorem. We motivate it by first making a definition. Maybe that green's hard to see, huh? Let Rn of x be the exact function minus the nth order polynomial, whether it's Maclaurin or Taylor, be called the nth remainder function. Well, you say remainder. The difference between the exact function and the approximation we call the local error in the approximation, the local truncation error, sometimes they call it in numerical methods. Function minus the approximation. All right. Now, with that in tow, it turns out you can prove this. If f of x has at least one derivative, one interval open interval, I better say, so that includes x and x. And suppose m is a bound on the absolute first derivative, m plus first derivative, at x0, point of expansion. Then it turns out that the absolute value of the difference, f of x, let's say f of x remainder, right? The most that your approximation can differ from your function in absolute value is m over n plus 1 absolute value of x minus x0, oops, to the n plus 1. That's a bound on the n. So all you have to do, if you can compute these derivatives and get a bound on the n plus first one, sometimes easier said than done, but on something like e or cosine, it's pretty easy, right? Then you can figure out this bound and figure out how many terms you need to get your error as small as you want. Right? So let's do this then. This theorem look okay. I'll leave the conclusion of the theorem up and erase all these hypotheses. That's a pretty strong result. Most of the persons are interested in science have lots of derivatives, not all of them, but a lot of them. Now get bound on approximations. All right, so here's an example. Find a bound on error in approximating cosine of 0.1 by the fourth order Maclaurin polynomial. That we just Yes, we're real close to the expansion point, right? The Maclaurin series is expanding at x equals 0. So this is really close, only 0.1 units away. Maybe it'll be a pretty good approximation. That's what we hope, right? Well, I have to erase that now, and we'll just put it up here and say, by the theorem, the error R n of 0.1 is less than or equal to m over, let's say R4 0.1 is less than or equal to m over 4 4 plus 1 factorial times 0.1. Actually, let's do this. I'm going to do one more step. I'm going to say R4. No, it's right. Times 0.1 minus 0 to the 4 plus 1. So there's the formula plugging in is 4 and x equals 0 since it's Maclaurin and 0.1 for x. So it's call it 4. I think it's 4 with expansion point 0 because it's Maclaurin. X equals 0.1 because that's what we want to use to make the estimate. And n equals 4 was the highest power that we allowed in the approximation. Well, let's see what's a bound on the fourth derivative. Fifth derivative. Right? Let's write this out. Where m is a bound, absolute value of the 4 plus 1 derivative at arbitrary point c over that's it. 4 plus 1 derivative, the fifth derivative, and an arbitrary point c. I'm going to draw it over here. Where c, that's what it looks like. 0 and 0.1. I should have written that in the theorem. The theorem says, in that theorem, you can compute a bound when the fifth derivative is continuous. You can say actually it has a maximum. So you can say the bound is the maximum. So for all our problems, it'll be, the highest derivative we need will be continuous, and then you can say it's the maximum. Remember how that works in calculus 1? You have functions that go up like this and don't have a maximum, right? Because they go up forever. Well, our functions will all be nice continuous functions they handle, so they'll have a high point. It'll be either an end point or a critical point, right? And so we won't do the what do you call them, pathological cases in here. We'll do engineering cases. All right. So there, m is the maximum value of the fifth derivative over the whole interval, right? That's what the theorem is saying. So what's the maximum derivative? I remember the fifth derivative. What is the fifth derivative? The fifth derivative, remember the fourth derivative goes back to the cosine. So the fifth derivative is the derivative of cosine of sine. Right? If we just take 5 derivatives, that's what we get. We already computed 4. And so if I just put c in here, Greek letter, I get c here. And how do I bound that? And I'm going to need to bound it value. Well, sine is always a number between plus and minus 1, right? So this is less than or equal to 1. So I can say that m is 1. So I'll put this in here, and the fourth Maclaurin polynomial at 0.1 approximates this to within 1 over 5 factorial. 0.1 to the fifth. You see why it's important to be close to the expansion point 0. If I were to expand this at x equals 100, I'd have 100 to the fifth power. I'd have a 1 followed by 10 zeros here, right? I'd have 10 billion multiplying this, and my error bound would be very high, right? But since I made the expansion point at 0, my distance from the point of expansion to the point I'm plugging in is only 0.1, and I get 0.1 of the fifth is 10 to the minus fifth power, 1/100,000. 5 factorial, by the way, is 120. Right? 1 times 2 times 3 times 4 times 5 is 120. So this is 10 to the minus 5 over 120. This is actually less than 10 to the minus 7 power, right? It's less than 10 to the minus fifth over 100. So I'm going to have a whole lot of significant digits in this, right? Cosine of 0.1 is about 0.1. Its first decimal place, I mean, it's just a little less than 1. So it's going to be like 0.9 or something like that. This says I'll have almost 7 significant, I'll have 6 significant digits because the error is less than 5 in the next place. That's the way significant digits work. If you write down the approximation, if the error with the next place is less than 5 in the next place, you say it's got that many decimal places. So this has at least 6 significant digits since it's less than 5 times 10 to the minus 7. If I could put 0.5 times 10 to the minus 7, I could say this has at least 7 significant digits. Now, bear in mind, this is just a bound, which means that probably actually this approximation does have at least 7 significant digits. So it's got at least 6 digits significant. All right, this looks like 0.9 something or 0.8 something. So you just count over 6 digits and then you're less than 5 error in the next one. So you say those 6 digits are significant. So at least 6 digits significant, probably more. This bound tends to overestimate in practice. Doesn't always. There are functions for which it's strict, but usually it overestimates. At least 6 digits significant, probably more. So that's a pretty good approximation when I'm close. Now, if I put, like I say, if I went out to 100 approximated, then I'd lose all my significant digits. I'd have to get a higher order polynomial approximation. I want to make one more comment on this, actually. Once in a while, you can do a little better. Estimation. Note if you take the cosine, that's 0. Cosine is minus the sine of 0. At 0 is minus the sine of 0. What does d5 of x look like? It's actually the same thing. It's 1 minus x squared over 2 plus x to the 4th over 24. Plus the next term is 0x cubed, 0x. And so actually the 5th degree polynomial is the same. Is 0. That's why we call this the 5th order approximation. The 5th order approximation is the 4th order approximation. Hence, the actual error bound is R5 of 0.1 also. This term is true. It's less than or equal to this. Bounded by an approximation we did because it's also the 5th order approximation. Like I say, it's also bounded by absolute value of R5 of 0.1, which is M for 6 factorial. 0.1 minus 0 to the 6, where M is a bound, we'll say maximum since it's a continuous function, it has a maximum, over all numbers C over the interval that and plug in, point I'm plugging in 0.1, absolute value of the 6th derivative of C. Like that. What's the sixth derivative? Well, the fourth derivative was cosine. The fifth was minus the sine. The sixth is minus the cosine. So this would be maximum over c between 2 and 1 of c. Bounded by 1, right? We can say what is it bounded on that. We could have actually done better on the sine because it's the interval always real small. We'll say this one is almost 1. In fact, it takes on the value 1 in this case at x equals 0. So in that case, I can say the error is bounded by, and with the same approximating polynomial, 1 for m over 6 factorial, 0.1 to the 6th. Well, 6 factorial is 6 times 5 factorial. 6 times 120 is 720. This is 10 to the minus 6. So look, it's almost 10 to the minus 9th error, right? So this is less than 0.5 times 10 to the minus. All right, that says we're guaranteed at least 7 digits. So if there's less than, oh, I'm sorry, 0.5, there's at least 8 significant digits. If it's 5 times 10 to the minus 9, then there's at least 8 digits. Okay, so we showed before there was at least 6, probably at least 7. We were close. Actually, 5 there's at least what you want is to count off from the first digit. This is right, 0.9 something. The first digit occurs in the first place to the right of the decimal, and you count off 8 of them, and there's less than 5 in the 9th digit. So you say it's got 8 significant digits. Those first 8 are good. Okay, any questions on that? That's going to finish the section. But we're going to come back to the stuff because, as I told you, we're now going to take these to infinity, right? It's like Buzz Lightyear. If you want me to not erase this too soon, I can leave it up a little longer. Now we're going to very briefly, because it's almost out of time, Taylor and Maclaurin series. In the Maclaurin polynomial, we have this, and I'm going to introduce what we call sigma notation. That's, I assume you've seen in calculus 2 already. Pn of x will be written as f of x0. Let's say from a polynomial. F of x0 plus f prime of x0 plus f double prime of x0 over 2 factorial. And I forgot this was x. Plus f double prime over 2 factorial. All the way through n derivative over n factorial times x to n. I'm going to write right on the Taylor polynomial, I'm going to write x minus x0. And oops, I like to put in 0 here too. Well, that's easy. Wouldn't it be nice if there's a shorter notation for that? Sigma notation says actually that I can rewrite this as sigma for sum, as capital sigma like you see in the Greek houses. K equals 0 to infinity, just like we've been doing on the infinite series here. But now we've got an infinite polynomial, if you like. It's not called an infinite polynomial anymore. It's called a power series. F K derivative Oops, I'm sorry. Thinking ahead. So for the polynomial, I just go k equals 0 to n. K squared at 0 over k factorial x to the k. Right? So here's a formulation that was mentioned before for ordinary series called. And that writes it with a lot less work. And then similar notation for general Taylor series. Taylor polynomials. Oh, I should write it down. Sum fk at x0 over k factorial x minus x to the k. Here's t n of x, same notation for the Taylor polynomial, k equals 0 to n. All right, so we have those. Now what we want to do is if we take the limit as n goes to infinity of these, we call those the Taylor and Maclaurin series. So write that down. And go to infinity in these. You get in the first case, equals sum. It's the limit of this, but the limit of this means you sum any patient for. This means the limit of the sum 0 through n. Fk of 0 over k factorial. I should put k equals 0 to the answer to k. Always. Fk at 0 over k factorial x to the k. For the Maclaurin case, all you do is replace n with infinity. Means take this one, limit as n goes to infinity. Now, the interesting thing is when you plug in a particular x0 like here, this is a number times the power of x, this is a number times the power of x. If you plug in a particular x in here, you just get a series that we've already studied. We can study whether these things converge for certain values of x and maybe diverge for other values of x because you get a different series for each x, right? So these are called power series. And this power series is called the Maclaurin series of the function. And if you expand it to another point, and like k go to infinity, and x0 minus x0 to the k. That's the Taylor series. That's what series and Taylor series goes to infinity. And for lots of functions, I've mentioned before with the cosine, this is exactly equal to the function if you let this go on to infinity, right? You can show that the further you go, by going far enough, you can make the error as small as you want. And consequently, we say the limit at infinity is exactly the function. Let's do the easiest one since I'm very short on time here. What is the Maclaurin series? One. Or e to the x. Maclaurin series for e to the x. We found out that the zeroth derivative at 0 is the function itself. Is e. The first derivative at 0 is e, and so on and so forth forever. All right, so if I take this formula and call that 5, with this until every derivative is e, we can say by equation 5, evidently. Oh, I'm sorry, I don't want this. This was for this is for the expansion at 1. So, right, the function example at x equals 1. The derivative at e to the This e to the x and so on. So at 0, this is equal to 1. 1 get e to the 0. The derivative at 0 is e to the 0 is 1. All the derivatives at 0. The nth derivative at 0 is equal to 1, and so on and so forth. Forever, all the derivatives are 1. That's what's nice if you take the Maclaurin series for e. Now what I have is I can write out a general formula. Formula is 1 no matter what. By 5, I have that. What's it called? Let's just take but equal when it was the polynomial. These are the corresponding series where you let n go to infinity. By 5, what we get is the series, the Maclaurin series for e to the x is e to the x 1, so it's sum k equals infinity 1 over k factorial. Okay? It's just this series right here. It means 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial and so on. If you let that go on forever, it gives you an exact expression for e to the x, and that is of real valuable theoretical importance in messing around with this thing. That's it for tonight. We're out of time. There's not too many of them. My book and couldn't find it anymore. It's at a 9.7. Try these on Maclaurin and Tayor polynomials. And you might look ahead at the next section that we just started. 3, 7, 9, 11, 12, 17, and 19. So not so many. You got 5 days to look at them and get back to me. And then we'll finish these next week and have these be on the last topic in the exam, the series and so forth, the next couple sections. Thank you for coming on tonight. Any last second comments? All right. See you next time.